section 12.6, properties of solutions. After this, go and check out video problems 69 and 70. So now we're going to talk about mixtures of a solute and solvent that can possibly be separated. So first, we've been talking about solutions. Now solutions cannot be filtered out, and they will pass through a semi-permeable membrane. So think about salt water, a saturated solution of salt water with no solid set at the bottom. If you were to filter that, you're not going to get the salt. You're not going to get the sodium chloride ions filtered out. Okay, you cannot, for a solution, you can't see the particles, and those particles are uniformly distributed. Now, a little bit larger than a solution is a colloidal dispersion, also called just a colloid. Now, these have larger particles. We still can't filter them out, but they will not pass through a semi-permeable membrane. That's because they're a little bit larger. Okay. If I mix it, the particles won't settle out, and we're usually talking about larger molecules or ions. Right. So some examples of colloids here. Fog is an example of a colloid. And let me mention real quick, there's something called the Tyndall Effect, Tyndall, the Tyndall Effect, and it checks for a colloid. So with a Tyndall Effect, what you have, so this one's a solution, this one's a colloid, okay, and what you do is you shine a light. So here's my drawing of a flashlight. You shine a light, and if you can see, what happened to my solution? If you can see the beam of light, it's a colloid. So in the solution, we wouldn't see the beam of light, but then through the colloid, we would actually see the beam of light. The reason why is because the particles are larger in the colloid, and since they're larger, light will bounce off of them. In the solution, the particles aren't nearly as large, and so the light will not bounce off of it. So that's one quick way to check for a colloid, which is also why you don't want to shine your bright lights when you're driving a car when you're in a fog, because the bright light will bounce off of the particles that are suspended. Right? And then finally, the largest type of mixture of solute and solvent is a suspension. So this is heterogeneous, it's non-uniform. You can filter it out, and you can use a semi-permeable membrane. It does settle out of solution. So think about muddy water. Right? If I had a jar of muddy water and I shook it, the quote-unquote mud particles would be suspended, but if I wait for a while, that mud will all settle out. Okay. A little bit of information, table 12.10. So here's the idea: solution, colloid, suspension. A suspension is going to settle out, a solution in colloid will not. You can filter out a suspension, you cannot filter out a colloid. And then finally, the semi-permeable membrane, the colloid's going to get stuck, the suspension's going to get stuck, but the solution can go in and out. Okay? Now let's talk about some other properties of solutions, and these are mainly going to be solutions, what we typically think of. So we're no longer really talking about colloids or suspensions. All right. So what we're going to be talking about are what are termed colligative properties, and colligative properties are properties that it depends on how much stuff is in there, not necessarily what type of stuff that's in there. So when you add a solute to a solvent, the freezing point will lower and the boiling point will get higher. So for instance, instead of freezing at 0 degrees Celsius, maybe it freezes at -10 degrees Celsius. Now that's advantageous when you have ice on your sidewalk. So you throw a little bit of salt on there, and that's going to lower the freezing point. It means it's going to freeze at a lower temperature than what it currently is, which is going to make it turn back into water, liquid water, which is now, you no longer have ice on your sidewalks. Okay. Raising the boiling point, so instead of boiling at 100 degrees Celsius, maybe it boils at 105 degrees Celsius. And again, going back to the idea of boiling point, it's the temperature that cooks the water, not the action of boiling. Okay. So it's the number of particles that we're concerned about, not necessarily the type of particles, sort of. One thing you have to remember is that a non-electrolyte, when you throw it in the water, it won't break up. So if I throw in 1 mole of C2H6O2, I get 1 mole of C2H6O2. But if I throw in 1 mole of sodium chloride, I actually get 2 moles of particles out. So the number of particles is what matters. So now I have, instead of 1 mole of particles, I have 2 moles of particles. So I get twice the effect. Calcium chloride, I'm going to get 3 times the effect, because now I'm going to get 3 moles of particles out. So when you go to look at salt in the winter, the cheapest stuff is rock salt, which is just sodium chloride. The more expensive stuff is going to have calcium chloride or aluminum chloride. And the reason why it's more expensive is because you need less of it. It has a greater effect on the freezing point of that water. Okay? So one of the units of concentration that we use for this is what's called molality. And the molality is the number of moles of solute divided by kilograms of just solvent. So it's moles of solute divided by kilograms of just the solvent. Now here's the relationship. The delta TF, which is the change in freezing point, let me jot that down here, change in freezing point, is equal to M, which is the molality, times Kf, which is the molal, in this case, freezing point, constant, so that has to be looked up in a text, and that depends on, that's up to the solvent, okay? And then I is the Van't Hoff factor. And basically, for instance, if it's sodium chloride, your Van't Hoff factor is 2 because it breaks up into the sodium ion and the chloride ion. If you have something like aluminum chloride, AlCl3, your Van't Hoff factor would be 4 because it breaks up into the aluminum and 3 chlorides. So it's basically how many particles you get out of it, right? Now delta TB, this one, same idea except this deals with boiling point. This is molality still. Kb is the molal boiling point constant. And you have that same Van't Hoff factor. Okay? So that's how you can calculate how much the freezing point is going to go up, or I should say how much the freezing point is going to go down, and how much the boiling point is going to go up. So that's one property, 2 properties I should say, melting point and boiling point, or freezing point and boiling point. Another property is osmosis. So osmosis is the passage of water across a semi-permeable membrane, and that's important to remember that osmosis is the passage of water. It is a special type of diffusion. Now in this case, what's being diffused is water. And if you know anything about diffusion, it's always from high concentration to low concentration. And in this case, what we're talking about is the amount of water. Okay? So here we have a semi-permeable membrane set up. Water can cross that. Sucrose cannot cross that. And so osmosis is going to occur. Water is going to go from lots of water to not as much water. So if these are level, which they are, that means that there are more water particles on the left-hand side than there are on the right-hand side. So on the right-hand side there are fewer water particles. So what will happen is that water will diffuse across this membrane and we'll end up with one level of water, pure water, and then the level of the sugar water, the sucrose water, will be higher. And the reason why is because of osmosis. Now, it'll stop traveling across this membrane when the atmospheric pressure won't allow it to come across anymore. And that's what's called the osmotic pressure. Okay, the osmotic pressure is the pressure I need to exert on this to get it to go backwards. So we can also say it's the amount of pressure that this is exerting right now. Okay. Now there's such thing as reverse osmosis, which when reverse osmosis, let me draw a U-tube. Alright, so there's a U-tube. Here's my semi-permeable membrane. If this is water, and this is, let's say, sugar water, then water is going to go across this membrane, and eventually what's going to happen is something that looks like this. I'm going to have a higher water level over here and a lower water level over there. Now, if I apply pressure on this, and I force it to go back down this way, to go opposite of osmosis, that's what's called reverse osmosis, and I have had to apply osmotic pressure on there. Okay, so at least osmotic pressure, because the osmotic pressure is the amount of pressure that this layer exerts. And then of course osmotic pressure plays an important role in biology as well. Here we see a red blood cell, and we're putting three different types of solutions. So we have an isotonic solution, which is the same concentration of water in and out of the red blood cell. We have a hypotonic solution where the concentration of the solution is less on the inside and then we have a hypertonic solution, which now we have a higher solute concentration than the red blood cell. And so what happens is water moves in and out of the red blood cell dependent upon the concentration of the solution. Okay?